this example, we are going to estimate exponential regression model, and we will compare it with a linear regression model and see which one does better. So the question is, why do we do exponential regression model? Why do we use this kind of estimation? For many reasons, basically. Maybe for handling skewed distributions, maybe for looking for the linearization of the relationships, or stabilize the variance, so something related to the homoscedasticity, or maybe some assumptions like normalizing the residuals. But mainly in this class, we are doing this just to look at the percentage changes. So transforming the response variable allows us to, or allows the coefficients to be interpreted in a way like as approximate percentage changes. And it's meaningful in some of the context, like this example. So first, we're gonna call the data. Let's read the scenario first. We have real estate people. Chad is considering real estate investment near a community college. The data includes monthly rent in dollar for 27 hours, along with 3 characteristics of the home: number of bedrooms, number of baths, and square foot. So let's look at the data. It's strange here. 27 houses, not hours. So first we look at the data. So we load it. We have 27 houses. These are the data, the rent, beds, baths, square foot. And it's a good idea to look at them. They are all numeric because we are doing regression. We make sure that all numeric, even the ones that are categoricals, we have to convert them to numeric numbers. The minimum, the maximum of the rent, number of beds from 1 to 4, baths from 1 to 4, square foot from this to this, and so on. So it makes sense, data is fine. After that, we're going to estimate both models, linear and exponential models. Again, we're going to repeat what we have done before. Linear model, rent is my response. I'm going to write this in terms of all of the other variables. We can look at the linear model. Also, let's run the exponential model. Let me take caps here. Linear model, or underscore, exponential model, LM, rent, tilde. Not rent, now we are doing the exponential, so it's log rent, sorry. Log rent. Beds plus baths plus square root, comma, my data. Someone's going to tell me, can we do dot? Yes, you can. So let's do this. Both are correct. Summary of X model. So this is the first model. We have one significance variable, which is the baths. Beds are and square foot are not. Adjusted R squared is quite good, 0.76. So 0.76 of the variations of the response is explained by the model. The second model, we have, again, the same thing. One variable is significance. By the way, both of them collectively give you that as a model, all of these variables, or at least some of them, contributing to explaining the response variable. And this is 70%. Before we had 76%, right? The error is 0.20. This one is 0. There, wow, is high. Yeah, but there's something, by the way. We have to say something here, and this is important. Here, the model, the values are calculated in terms of y, which is the rent. So this is 0.76 is the adjusted R squared for the response variable, which is y here. And here, the 0.70 is the adjusted R squared for the log y, log rent, not for the rent. So we have to find the adjusted R squared for the rent, not for the log rent. So this model, we have the coefficient, the baths is significant. We said something about the R squared again. So this is the adjusted R squared, 70%. This is for the log rent, so we have to be careful here. We have to compute the R squared for the rent, not for the log rent, not for the log rent. But before we do this, because the question now first says we have estimated both of them, that's it. We will not comment on any of the values of the R squared now. Now let's do some prediction. So predictions. I forgot how many. So you have 2 here, doesn't make sense here. So this is 2. This is 3, this should be 3. third header. This should be also 3. So compute the predicted rent for 1500 square foot house with 3 beds and 2 baths for both of them. The question says ignore the significance test. We will not do a significance test. We will not rebuild the model. We have only just 2 or 3 variables, so there is no need. So what we are going to do, we are going to do the prediction for the y, right? For the linear model. So predict linear model data frame. We're going to plug in these values into the data frame. Beds have to be 3, baths have to be 2, square foot have to be 1500. So a house with these features is going to be $1,832, the rent of this house. Let's do the prediction for the exponential model, and we have to be again careful here. X model data frame, and beds equals 3, baths equals 2, square foot equals 1500. So this is the exponential model. Let's run both. As I said, this gives you, let me just say, hold on, let me say something. This is basically what you are doing. You are plugging these values into the exponential model. Someone's going to tell me, what is the exponential model? Let me go up and write down the model. The estimated model. What is the estimated model? It is log hat log rent. The intercept 6.29 plus 0.132 beds, just to quickly, plus 0.19 baths, plus 0.0002 square foot. So this is, oh, hold on, I did not close this. Let me close it here. Let me take this one off. Here we go. So the log rent hat of the log rent equals this. So when you plug in, when you use the predict function, this is important. When you plug in the predict function, so it's going to calculate the log rent. So this is the log rent here. Let me run this. So the log rent equals 7.4. So the question is how to get the rent, the expected or the estimated rent for 3 beds, 2 baths and 1500 square foot house. We are going to calculate the y, or the rent hat. Let me call it rent hat, which is the estimated rent. Using this formula, and you can go back to notes. We can go back to note. So I'm going to call this, to make it easy. So this is the len y, log y. This is log y. The exponential of log y. Someone's gonna tell me why you didn't give claim for the first one. I don't need. So this is the rent. This is the estimated rent. This one you call it estimated log rent. So exponential of the estimated log rent plus the exponential model. You can only take the value called sigma, which is the SE, sigma of the exponential model. You square it, you divide by 2. So this formula does exist in the notes to get the rent hat, or estimated rent, because we used estimated, so I'm going to take off the hat. Hat means estimated. So the estimated rent, sorry for this confusion, but assigning names sometimes challenging. So this is the estimated rent. So let me copy estimated rent. Oh, we have to estimate rent. So the estimated rent for the linear model, sorry for this. And this is estimated rent for the exponential model. And let's see both that. So let me recap. Estimated rent for the linear model for these values, 3 beds, 3 baths, 2 baths, etc. We got this value. Then estimated rent or log rent is this. We don't need this, so that's why we need to calculate the estimated rent for the exponential model. We use this formula, which is the exponential of all of these. After that we run. Now makes sense. So the first one is the estimated rent for the exponential model, which is $1,846. Second one, $1,832. Now the question says use R-squared to select the appropriate model. So which one is better for the prediction purposes? Do we have to take the first one or the second one? So that's why when I talked about here the R-squared, we have no problem with this R-squared because this is R-squared for the response variable, which is rent. But here they are squared for the log rent. How do we calculate R-squared? R-squared is just nothing but the correlation squared. So we are going to do two things. First of all, we're going to find the standard error. The standard error is sigma exponential model. So first, what is sigma of exponential model? What does this give you? This gives us the standard error of the exponential model that we built, this one, the one that we built. After that, we are going to find the predicted y, predicted y, or predicted ln y. So what does this give you? Let me show you what does this give us. If you do prediction for the exponential model, it gives us all of the ln y, or all of the estimated ln y, all of the estimated ln y. After that, we are going to do this we are going to switch this to transform this to y. We need to find the predicted values of the y, the rent. What is y? Is the rent. We can keep it y. We use the same formula. Exponential, predicted ln y, plus the sigma, this one, as we did, sigma, which is the SE, squared over 2. So we are converting every single point here, the log y, into y value. So basically, what is this? Do you have a problem with the, yes, let's close the parentheses. Here we go. So what is the predicted y? Let me copy it and show it to you. Now do you remember these? These are the log rent, the log y, or the ln y. Ln is the natural log, and which is the one that we use. Log in R, it's the natural log, or the natural log. So this is the log of the rent values for the 27 houses, the estimated ones, and these are the estimated rent values, using this formula. It's a mathematical formula. So after that, what we do, we find the correlation between these two. No, we find the correlation between my data rent, the observed rent, and the predicted y. We find the correlation between the observed and the predicted, then we square it. This is going to be what? Our adjusted R squared. I'm going to call it adjusted R squared. It's 81%. So the adjusted R squared for the first model was 70%. For the second model is 81%, not 70. So the first one was 60, sorry. The linear was 76% for the linear. For the second one, it's not 70%. No, this is for the log rent. To find the R squared for the rent, we did all of this. We got 81%. So as a result, which model is better? So the second model does better than the first model. So it is more appropriate for prediction. Yeah, so this is everything. Thanks.